together. Okay. No, this is not moving. And that's good. It's moving. Okay, it's moving now. Okay, very good. So that's for that. So you can see we can all see the screen, right? I want to assume we can see the screen. I want to believe that we can see the screen. Can we see the screen?
Yes, sir.
Now look at chemical bonds there on the screen. Chemical bonds basically means the attractive force holding two or more atoms together. Remember, as part of uh, the introduction into this topic, I already said that the definition is basically from the name. When we say something to bond together, it means some things came together to to form something. It's just like someone doing wedding now, for example, like in a car or something. So it's a marriage, right? And it's a bond for life. So you have two different or two entities coming together to become one. That is exactly the same thing that applies here. Just that this has to do with chemical elements or chemical substances. So yes, chemical bonding, it means two atoms combine together. And for these two atoms to combine together, there is some kind of a force of there's some kind of attractive force that holds those atoms together. So it may be two or it may be more than two. So you may have two atoms or more than two atoms. So that's just definition. So basically you should know that there are three kinds, as you can see here. So you have the covalent, you have the ionic, and you have the metallic. Yes. So talking about covalent, it basically results from equal sharing of electrons between the atoms, usually found between non-metals. So you see covalent bonding between non-metals. So for example, hydrogen atom combining with hydrogen atom to form H2 hydrogen molecule. That is a covalent bond there. Hydrogen combining with chlorine to form hydrogen chloride gas, which in solution forms hydrochloric acid, is also um, a covalent bond. Like it's a covalent bond that holds those atoms together. Now, this covalent bond of a thing can be related to real life examples in a case where husband and wife are sharing things equally. Like how should I put it now? Like there's already an agreement term that okay, you will take this, I will settle this. You support this, I'll support with this. So that equal sharing or equal distribution of activity or of responsibility is kind of synonymous to equivalent nature. Yeah, so that's about that. So you should know that between these non-metals we are talking about, one one of them is um is usually considered to be uh okay, don't let me go there. We are still going to look at that later in the presentation. So ionic bond, you have ionic bond result from the transfer of electrons from a metal to a non-metal. So this one is from a metal to a non-metal. Remember when we were discussing the periodic table, we said the metals occupy the block one, uh, I mean the group one, group two, some of group three, and you have the transition metals in between. Am I right? You have group one, you have group two, you have some of group three. Let me say group three, but not all of them are that metallic in nature. And you have transition metals in between them. So it is expected of you that you also know those periodic table that was discussed before. So this ionic bond results from transfer of electrons from metal to a non-metal. So for example, sodium transferring a single electron to chlorine. Are we together?
Yes,
Okay,
sir.
okay. Now metallic bond, that's an attractive force between or holding pure metals together. You know, metals basically they have, when you look at metals, for example, iron, for example, iron is not just like how should I put it now? Iron definitely has um some minute components. So the way you see iron is not just uh, a solid structure. Like every solid structure you see has a minute component that come together to make it a whole structure. So that iron, as we've seen there, you're definitely gonna you are definitely going to agree that it's a very hard metal, and um that hard nature or that hard structure is is made up of certain components that are combined together, held together by some certain forces that make it that strong. So that kind of force holding the metals together, like metal, just a pure metal, just one metal. When we say pure, it means it's just that single substance there. So it's the metallic bond is now the attractive force holding the pure metals together in the crystal lattice, or in the lattice structure. Let me put it out. So the next one, okay. So talking about ionic bonds in more detail, is it is the kind of bond you see between metals with low electronegativity. Yes, it should be noted that metals, they have low electronegativity. You can't compare them to non-metals. Non-metals do have high electronegativity. So remember the periodic table, we mentioned that electronegativity varies, like it increases as you move from left to right on the periodic table. That is, when you're moving from left to right, electronegativity increases, right? But if you're moving from top to bottom, electronegativity decreases. When you move from left to right, you're moving from metals more to non-metal side. So that is why. So metals should be considered with they are considered to have low electronegativity. Why? The reason for that is because they don't have much tendency of attracting electrons towards themselves. Rather, they want to give out, right? They don't have much uh, affinity for electrons. Rather, they want to give out. So what they have is now ionization energy. I don't know if we get what I'm trying to say. Anyway, so we've discussed that in periodic table. I'm still going to ask questions as regards that. So you should know that it exists between metals and non-metals. So those metals are considered to have low electronegativity, and the non-metals, they are those with high electronegativity. So it usually involves electron transfer. So there's usually an electron transfer from one of these groups, usually the metal, to the other group, the non-metal. Okay. So it is held by strong electrostatic force of attraction, which exists between oppositely charged ions. So when you look at metal, it's a positively charged ion. When you look at non-metal, a negatively charged ion. So when they combine together, for example, sodium ion and chloride ion, Na plus combined with Cl minus, when they combine together, the force of attraction holding those oppositely charged ions together is referred to as the ionic bonding. And also it has the highest tendency will be between elements on the bottom left and those on the top right of the periodic table. Yes, I don't know if anyone understands what this is trying to say. When you look at the periodic table, the elements you see, like the element you see on the bottom left, are having greater tendency of combining with those on the bottom right of the periodic table. And that's due to some of those properties that we mentioned in the periodic table that varies across the period and down the group. Okay. So moving quickly, e.g. NaCl is an what's it called now? Ionic compound. I shouldn't forget. Ionic bond give rise to ionic compound or ionic molecule. The bond is ionic bond, while the structure that is formed after the bonding is ionic molecule or ionic compound. So NaCl now, this is an ionic molecule. So you have the sodium what's it called now? Electron configuration there. 1s2, 2s2, 2p6, 3s1. So that's a total of 11. 2 plus 2 plus 6 plus 1. That's a total of 11 valence, sorry, 11 electrons with one valence electron here, this one here. And the sodium ion, that's a cation, which is formed just when this single electron is given off. When this one is given off, then you have 1s2, 2s2, 2p6. So for chlorine, this is chlorine 17, right? And the atomic number is 17 rather. 1s2, 2s2, 2p6, 3s2, 3p5. When you sum up everything together, so it's 17. And this wants to gain an electron. So it's going to gain the electron from this sodium here. So once the electron transfer to this place, you can see the chlorine now becomes negative. Negative, that is anion, which implies that it has gained one extra electron to what was there before. The number of electrons that was originally present was 17. As soon as it gained one more electron, it becomes 18. When you have 2 plus 2, 4, 4 plus 6, that is 10, plus 2, that is 12, then plus 6, that is 8, 18. Remember that we are not adding all this number 1, 2, 2, 3, 3. No. We are instead adding the powers of those subshells. This one is 1s2. It's meant to be a power there, but because of the presentation is why it is written this way. So now, what is actually the purpose of bonding, of chemical bonding? You should know the purpose. And the purpose of chemical bonding basically is just to what? To stabilize, like for stability. The purpose of chemical bonding, once again, is to stabilize an atom or for the stability of the atom. So for chlorine to be involved or to want to gain an electron here is because it is unstable. So as soon as it's able to get a single electron from any metal that is ready to give it out, then it receives. And then once it receives, that neutral atom now becomes a negatively charged atom called the anion, as you can see here. So electron gains or lost in order to achieve the octet. Yes, you should know that. The octet is a full configuration, that is for an atom that is stable, or a noble gas configuration. You know that all the noble gases are stable, right? So those ones that they are not involved in any form of chemical bonding. Why? Because they are stable. So every other element that are involved or that are participating in this combination is for the purpose of attaining or achieving stability or achieving the noble gas configuration. That is the stable atoms. Okay. So using the Lewis structure, yes, Lewis is able to from the Lewis you're able to point out, okay, where is the which one are we donating out, and also where is the electron going to. So usually when you're drawing Lewis structure, the atom, look at sodium for example now. This sodium atom has four directions. What do I mean by that four direction? There is a direction up, there's a direction to the left, there's a direction downward, and there's a direction to the right. I will come again. Look at sodium. When you write sodium, or if you write chlorine, it has four directions. Above it, or at the top, away from it, or to the left, downward, or to the bottom, and then towards the right. you have those directions. So those directions, two electrons can surround them. Like in those directions, maximum of two. Okay, don't let me say maximum of two. Two electrons can occupy those directions or those positions. Two, two, two here, two here. What's that telling you? Those electrons that you're going to put around the atom is going to be the outermost electron. Okay, so sodium, for example, the configuration is 281. Let me try to get my writing board. Hello, can we see hear me right?
Yes, sir.
Okay, give me some minutes. Let me connect a board. Uh, let's come here. Uh, okay, we can kind of manage this space. What's going on? Okay, can we see the screen?
Yes, sir.
Okay, so what I'm trying to say is that when you have an atom, for example, whether you have sodium, whether you have chlorine, if you want to write the Lewis structure, the Lewis structure is usually to indicate the number of valence electrons, to indicate the number of valence electrons around an atom. So as I've mentioned earlier, this sodium now, there's a direction here, point upwards. Okay, let me do it this way. There's a direction here, point to the right. There's a direction here, point to the left. And there's a direction here, point downward. Okay, this point downward. So those directions that I've indicated there can be occupied by the valence electron. Now you now need to ascertain what is the valence electron of sodium. Sodium itself is 281. That is 2 in K shell, 8 and 1 in the what's it called now? In the L shell. So 281 when you draw the structure. Chlorine. Chlorine is 287. So which tells you that this one has a valence electron of 1 and this one has a valence electron of 7. One valence electron you have there. This 7 valence electrons you have there. So if I want to draw the Lewis structure for sodium now, I may decide to write this. I may decide to do this. I may decide to do this, that is at the bottom, or I may decide to do this by this side. Do you get my point? That one there is not that you are going to indicate the total number of electrons, oh, please. It is just the valence electrons they are dealing with, okay? So you're dealing with 1 in this case, and you're dealing with 7 in this case. So we want to draw the valence structure for chlorine now. How many electrons do we think I'm supposed to put around it? Anybody? Are we there? Hello? Are we still
Hello?
connected?
Yes, sir.
Okay,
Yes, sir.
Yes, sir.
okay. So I mentioned something that if I'm to draw the Lewis structure for chlorine, how many valence electrons do we think will be around this chlorine atom here? According to what I've explained.
7.
7, thank you. So the seventh, what you're not going to do, you fill it one by one. You say 1, you say 2, you say 3, you say 4, you say 5, you say 6, and then you say 7. So this is the Lewis structure for chlorine atom. That is the structure. So you only just going to put 7 there, not the whole 2 plus 8 plus 7 there, please, not the whole 17. It is just going to be the number of the valence electrons, right? Thank you. So now back to the explanation we're given there. Uh, where is what I was presenting now? Where is it? Okay, that should be here. Yeah, here. So no, not this place. Let me clear some of these things that are too much here. Okay. So that is why you see this structure of chlorine to be that. Are we getting what I'm saying? That is why you see the structure of chlorine to be this, and then you see the structure of sodium to be this. So when they come together, you can see this one is going to donate that electron to this one. Are we together? It's going to donate this electron to this one. So once it donates, because sodium has now lost 1 electron, it becomes sodium plus. That plus one, this plus one there, indicates that it has only just given out 1. That is why you have it written this way. Why this Cl minus 1 or minus, you don't need to indicate the word, you just put minus there, indicates that it has gained just 1 electron. So this tells you that as you can see what the notes that is written here, sodium contributes electron, leaving it with a closed shell, as you can see here. Chlorine gains electron, leaving it with a closed shell, as you can see here as well. So in ionic bonding, please note that there is no sharing. They are not sharing. Rather, one is donating and the other is receiving. Are we clear?
Yes, sir.
Okay. Now also in calcium chloride, calcium is a metal, chlorine is a non-metal. So of course, the kind of bonding you're expecting here is an ionic bond. So when calcium reacts with chlorine, both electrons from calcium must be lost. So we can need 2 chlorine atoms to gain 1 each. So as you can see, that is why we have Cl2. Normally, some of you might be like, okay, the name of calcium is okay. Sorry. So normally, some of you might be like, okay, the chemical formula for calcium chloride is meant to be CaCl. No, it is not CaCl. That is not correct. Because if you understand chemical bonding very well, calcium is usually Ca2 plus, right? And this one is usually Cl minus. Even from principle of valency, you are expected to know that they are going to exchange their valencies. Like in Ca2 plus is having a valency of 2. In Cl minus, it is having a valency of 1. So they are just going to change their valency. So when they change valency, basically what you're going to form is just going to be CaCl2. But when you're looking at it from the bonding end, normally calcium has to lose two valence electrons. So to combine with chlorine, only just one chlorine can take one each. So mean that we're going to require two chlorines to make that combination possible. Okay, so that's about that calcium chloride. So you have that there. So the oxidation state of various elements, group 1, 1, 2, 3, or you have them to be plus 1, plus 2, plus 3, respectively. Okay, so do you expect the oxidation number of sodium to be plus 2? No, it is always plus 1. For calcium, it is plus 2. For aluminium, plus 3. How about for group 5, group 6, group 7? So please take note. There will be negative 2, negative 3 rather, negative 2, and negative 1 respectively. What do we call group 1 element again? What's their name? Anybody? What do we call their name now? Nobody is saying anything. Can we hear me? Hello? Ah, what's going on? Hello?
Yes, sir, we can hear you.
Ah,
Sir,
and you were not responding before. Why? I thought you guys couldn't hear me anymore. Okay, I was asking, what's the alternative name for group 1 again? What do we call group 1 element again? What do we call group 1 element again? Nobody? Is Adibasharu there? Is it a network? Hello?
yes, sir, we can hear you.
I was asking a question, nobody was responding. I said, what do we call the name of group 1 element again?
Alkaline metal.
Yes, alkaline metal. How about group 2?
Alkali earth metals.
Okay, how about group 3? Group 3, what do we call it? Just aluminium family or boron family now. What do you call group 5? Group 5 or group 15? Same thing. Oh yeah, quickly, time is going. You have just less than 12 minutes to the end of this session, or less than 15 minutes rather. What do we call group 5 or group 15? That's nitrogen family. What's the alternative name?
Sir, I don't know.
You don't know. Okay. I thought I mentioned it the last time. Nitrogen. They are the one we call nitrogens. This is the spelling. Nitrogens. That's for nitrogen family. Don't call it pnictogen. It's nitrogen. The P is silent. That P is silent there. You have chalcogen. I want to write chalcogen there. Sorry. Chalcogens. That is oxygen family. That's oxygen and sulfur. They are the ones that occupy the group. You have the halogens, right? Halogens. This is fluorine, fluorine or chlorine family. Okay. So quickly, let's get back to presentation. Actually, we won't be able to finish this presentation today. Likely, we're going to continue the presentation next session. So yes, group one, you should know the organization number. That's plus one. Group two, you should know the organization number as well. That is plus two. Group three, you should know the organization number as well. That is plus three. Group five, you should know that is negative three. For example, nitrogen is N3 minus. Okay. Um, chalcogen, that's group six. It's negative two. Example, O2 minus, that's oxygen 2 minus, S2 minus, that's sulfur 2 minus. Group 7, that's halogens. So you see that to be negative 1. So you can see chlorine, chlorine minus, fluorine minus. However, the transition elements can have various oxidation numbers. It can have various oxidation numbers. So you can have ion occupying, like having two various oxidation states. Ion 2 plus, ion 3 plus, Fe2 plus, Fe3 plus. It implies to you that just iron alone can have plus 2 oxidation states or plus 3 oxidation states. Copper as well, you have copper 1 plus, copper 2 plus, telling you that copper can exhibit plus 1 or plus 2. It varies, okay? So you should know that that of the oxidation state of transition element is not fixed, it varies. Are we together? Are we together, please?
Yes, sir.
Okay. So next is the properties of ionic compound. So usually they are solids at room temperature. They form a giant crystalline lattice or network structure in an ordered continuous structure. That uh, i.e., an ordered continuous structure. So they have that large or giant crystalline lattice structure, and usually they are solid at room temperature, very strong. They have very strong. They are very strong, and as well high melting point and boiling point. Like the example I made use of earlier, iron, for example, is very strong, right? So that's because of the strong force of attraction that exists in the sorry, ionic compound. Sorry. Sodium chloride, for example, yes, very strong, and you expect it to have high melting point and boiling point, right? They are hard and brittle. Yes, you also need to know that they do not conduct electricity when you have it in solids, but they do conduct in molten state or in aqueous solution. So look at sodium chloride, for example, the normal source, the normal table source. You don't expect it to conduct electricity in the normal solid state. However, if you put it in water solution, if you pass electricity through it and you touch it, you definitely, of course, going to observe that it's it's able to conduct. Okay, or when it is in multi-state. Multi-state meaning when it is like in semi-solid form. So they are more soluble in water than in any other solvent. So because of that, we refer them to as polar molecules. So they are polar molecules. Polar molecule because they dissolve in a polar solvent, right? So that is that. I hope you are understanding what I'm trying to say.
Yes, sir.
Okay. So and then here you have the lattice structure of sodium. So you have the sodium in these purple balls here, Na plus, and you have the chlorine in this green structure, Cl minus. So this is the structure of sodium chloride. You can see this large or giant lattice structure. So and they are held together by this bonding that we're talking about, the ionic bonding. As mentioned again, they are hard and brittle, very strong. They do not conduct electricity in the solid state, but when you have them in molten on an aqueous solution, they are able to conduct electricity properly, right? Also, they have high melting and boiling point. High melting point means that you require a significant amount of heat to melt, a significant amount of heat to convert this to a liquid state. Okay, and also you require a significant amount of heat to cause it to 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 eat up as well, or to boil. So yes, having done with that area, you also need to know what electronegativity is all about. So quickly talking about electronegativity, it is the ability of one atom in a molecule or in a bond to attract electrons to itself. Any one of you recording this session? Do we have anyone recording this session at all? Nobody. Okay. But can we still hear me? Okay. Good. So talking about electronegativity, the ability of one atom in a molecule or in a bond to attract electrons towards itself. That is electronegativity. Electron negativity. So just kind of know that yes, it has to do with electrons. Okay, that is one. Now, being negativity is like being, how should I put it now? Like being hyperactive for electrons. Like when we say something is too active, so they really want to attract or want to get electrons towards themselves. So that is electronegativity property. So again, the ability of one atom in a molecule or in a bond to attract electrons towards itself. So you need to know that on the Pauling scale, there's a scale that shows is a table, like a kind of a table for electronegativity's value of uh of what's it called now, of elements. Yes. So this Pauling scale, yeah, it also has a periodic, like, how should I put it? It's more like the periodic table and then they put the electronegativity value there. So Pauling set electronegativities on a scale from 0.7 to 4.0. So this means what to you? It means that the least electronegative element on the periodic table is cation. The least electronegativity element on the periodic table is cation, CS, having a value of 0.7, and the most electronegativity element on the periodic table is fluorine, having a electronegativity value of 4.0. Okay, so you should expect that electronegativity increases across the period and down a group. But down the group, you expect it to decrease. Okay, let me see if we have, yes. So you expect it to increase across the period. That should be an error, and then decrease down the group. Increases across the period, decreases down the group. Are we together? Okay, so see that we can't finish today. So I will have to stop it here. Now look at this scale. This is like the Pauling scale, as earlier mentioned. That the Pauling scale is not like the periodic table, but with their electronegativity's value there, you see they are being graded, right? Look at fluorine. Fluorine is the most is highly electronegative, so you have it having 4.0 there. I said it's about 4.0. And then look at calcium. Calcium is in group one. Look at the position. It's having electronegativity value of 0.7. So 0.7 compared to 4.0. So you can see that it is a wide margin. So any question of questions so far, we'll continue from where we stopped now next class. So please note this color pattern. Those with orange, that's from 3 to 4. Those with yellow, that's 2 to 2.9. Those with this light green structure, that's 0.5 to 1.9. And those with this kind of a purple color, less than 1.5. Any question or questions so far? Questions from anybody?